What are statistically designed experiments and why do we do them? Those are the questions I want to explore in this talk. When I hear the word experiment, I think of science. I don't think of statistics. So let's think about a scientific experiment. Typically, we conduct these types of experiments because we have some type of hypothesis that we are trying to verify, or maybe some other type of goal that we want to establish. It might be that we want to determine a particular parameter, a particular scientific quantity, and we want to get a level of precision that's better than we've had before, as one example. So we are motivated to conduct the experiment based on scientific goals. We design the experiment based on our scientific understanding of the mechanisms that we're investigating. And the purpose of the experiment is to collect data. And we then interpret that data based on our scientific understanding. There is another step to this, and it comes at the very end. Once we've analyzed the data scientifically, we have to try and qualify that data. So what do I mean? Well, typically, we conduct the experiment to determine a particular piece of information. In this experiment, I've got some number that I've measured. The final piece of the jigsaw is to then say, well, I have to qualify it. I have to say to what level of precision, how confident am I in this experimental result? Now, for me, this was always the point at which we did statistics. It was at the very end of the process in order that I could quote a result. Design of experiments, statistically designed experiments, looks at the process by which I calculate this precision, and it allows me to reverse engineer the experiment in order for me to get the optimal value for that statistic for a certain amount of experimental resource. So that's to say, I can try and design an experiment based on statistical understanding, based on how I'm going to analyze the data, in order to ensure optimal statistical outcomes. That might sound abstract, but I'm going to give you some concrete examples of this. I want to look at 3 arguments that illustrate and justify these statistically designed experiments. Let's take a look at the first one. We can often, in science, have a situation where the goal is to measure the slope of a line. So hopefully we're familiar with the notion of the equation of a line. A simple example might be Ohm's law, V equals IR. So if I draw a graph, then the slope, if this is the current and the voltage, then the slope is going to be the resistance. Even if I have a non-linear relationship, I can often transform those relationships so they do look linear. So let's take a look at a couple of examples of doing an experiment based on this. Now, what do we mean by an experiment? Well, as the experimenter, I have to decide, I've got an X and a Y. So the X is what I'm controlling, and the Y is what I'm observing. So I have to decide at what values of X I'm going to make measurements. So I've chosen to make measurements at these 4 levels. I might get some results that look like this. And then I would fit a line through those data points from which I can determine the slope. That's one experimental strategy. This is an example of this type of data being analyzed in JUMP software. So I have an estimate of the slope. So that estimate, let me make a note of it, I'm going to need it later. So I've got 0.02 plus or minus a standard error that's associated with that parameter estimate. 0.0011 is 11. Could I do the experiment differently? Well, yes, I could. If I understand how this number is calculated, then I would understand that this number depends on the configuration of these 4 data points. I could change that configuration to look something like this. Now my parameter estimate is pretty much the same, but my standard error has gone from 0.0011 to 0.0007. So if you like, we've gone from 11 to 7. The same amount of data points, we've just changed the configuration of the measurements. So this is an example where understanding how we're going to analyze the results allows us to reverse engineer in order to get a better answer. Now, you could argue that the experimental configuration on the right-hand side has got a weakness associated with it because I can only fit a line, I can't fit a curve. But if I know the relationship is linear, why would I want to fit a curve? And even if I don't know it's linear, sometimes a linear model is sufficient to get the answers that we need. But there are other design strategies that do look at nonlinear behavior, curved relationships. So I've got 4 different strategies here. The top 2, the one we've just looked at, the bottom 2 are alternative strategies. The bottom 2, the one on the left, could be considered an illustration of a so-called classical design. It could be a factorial design with center points or a response surface design. These are so-called classical designs in the sense you can find them in textbooks. One of the features of them is they have a certain symmetry associated with them. And that symmetry was designed in specifically because we used to use these designs before we had laptop computing. So we had to do the analysis calculations by hand, and we can exploit symmetry. Custom designs are computer-generated designs. Because we're doing the analysis on the computer, we're not constrained by the requirements to maintain symmetry. And actually, although the design on the right-hand side might look a bit strange and lopsided, it gives us a slightly more precise answer than the design on the left-hand side. So classical and custom designs is one way of thinking about different types of statistically designed experiments. There's a more general classification, which is thinking in terms of screening designs and response surface designs. So screening designs only allow us to look at a linear effect, whereas response surface designs allow us to build a more refined model. I can express this slightly more mathematically, or at least with a slightly more mathematical notation. This is the standard equation of a line. We can generalize that for multiple x's. And we can think in terms of estimating these parameters for the x's. These are the slopes, if you like. And screening designs have the intention of maximizing the precision of those parameter estimates. Whereas response surface designs look at the precision associated with the y value, the predicted value. Now, it would be reasonable to think that if you maximize the precision of these parameters, you also maximize the precision of this, but that is not true. And because it's not true, we end up with different flavors of designs depending on what the goal is. There is a famous quote that says that all models are wrong and some are useful. So one of the most important things is we have to think about why we are doing the experiment. What outcome are we seeking? And that helps determine which type of design to use. But again, before we think about that, let's come back to the arguments for different design strategies or experimental strategies and how statistical thinking can motivate us to improve the experimental strategies. Let's think about this problem where I have 3 unknown weights. In many ways, it's the most trivial problem I could think of in terms of conducting an experiment. The experiment, of course, is to just take a balance. With that balance, I'm going to take one of the weights and put it on one side of the scales. Then I need to counterbalance it. That looks like it's just gone too far. Let's try put one over here. And no, I think that's maybe only needed a half there. So it's just, well, let's take this off. Okay, so now let's put a half on there. So I think what I'm going to say with this is it's about 14.5. I'm not going to bore you with the other measurements, but let's just say this is 25 and this is 20. So this is almost so trivial, we don't think of it as an experiment maybe, we're just taking measurements. But it is an experiment, and by an experiment we have to make a conscious decision about how we actually conduct the measurements. What have I achieved here? Well, what I've really achieved is I have got measurements for each of the weights, and there's some precision. The precision might be, we could say the precision is plus or minus 0.5. That was the smallest weight I could actually measure on here. But more generally, I can say it's plus or minus sigma. There's a certain experimental error associated with this procedure. Part of that is due to my ability to perform the experiment, but also the tolerances associated with the scales. What do I do if I want to improve that precision? Well, there is a very standard experimental procedure, and that experimental procedure is just to repeat all of the measurements. So what I could do is say, well, the first time I got a value of 14.5 here, I'm going to repeat the experiment. I'm going to measure it again. But actually, if I think about this, there might be a systematic bias between left and right. So maybe I put the weight on the other side and now do the counterbalance. That looks pretty good to me. There's even a temptation that might be a little bit like that, but I think that's going to take it too far. Yeah, I think that's a bit too far. I'm going to take it at 15. So now I've got a 15.0. So what would I say in this instance? I would say I've got the average of those two, which is 14.75, plus or minus. Well, what's it going to be plus or minus? Well, actually, if you do the maths on it, it's sigma divided by the square root of 2. So I have reduced the standard error, so I've increased the precision by a factor of root 2. How have I done it? Well, I have gone from 3 measurements to 6 measurements. So there's a certain cost or a certain time in order to improve that precision. But is there another way? Could I have done this in a different way? Well, it turns out I could. There's a different experimental strategy. I could take this measurement, but instead of that, I could put the green here, and I'm also going to put the blue. Oh, okay, so the blue is very heavy, so let me try and counterbalance this now. And maybe there's a 2 that comes onto here. And another one. So you get the idea. What I've done is to measure the difference between the red and the green plus the blue. Wow, okay. So what am I going to do with that? Well, I can't do much with it without doing some much more, more complex maths. We have to do some algebra. So I'm just going to show you that what I have done in the first measurement was to take the red and the green minus the blue. Okay, I did it slightly differently. So that red and green minus blue would actually be a slightly different configuration, but it's the same idea. So if I just reset, it's the red and the green. Well, let's put the blue on. So the idea is I put one of these on the other side, and then it probably would have been apparent, okay, I need to put the green one there. So that's the thing I'm measuring. I'm trying to counterbalance this. It's less than 5. Let's say it's 4. So this particular one would be 4. We would then do red, and then instead of green, we'd do blue, and then green over here. And we'd get a different number. So I would have 2 different numbers there, which I can then plug in to those 2 values, take the average, and that gives me the mass for the red. But when you do the calculation, this is a bit like an average calculation. So this has got a precision of sigma, this has got a precision of sigma. The final result has got a precision of sigma divided by root 2. More complex analysis. But if I understand this analysis and how the calculations are done, then I can benefit from this. And what is the benefit? Well, both strategies have improved my precision. But the one factor at a time required 6 measurements, whereas the second strategy, which I'm calling the DOE strategy, required 3. Why have I called the second one a DOE strategy? Because we've reverse engineered the statistics to optimize the experiment. We are trying to get the maximum precision. We can always increase the precision by taking more experiments. So the question is, for a certain cost, a certain time, a certain number of experimental runs, what's the maximum precision I can achieve? And the interesting thing is, we achieve it by not doing one factor at a time. If we vary multiple things simultaneously, we increase the overall precision. So that's a very powerful argument for not doing one factor at a time. There's another argument, which is a more common argument you will see, which is to do with how we do optimization. So let's look at this third example. And let's imagine this contour plot is the expression of a reality, but it's a reality we can only discover through experimentation. So let's try and do that experimentation. And we'll do the experiment using one factor at a time. So the first step here, step 1, is we are going to fix the temperature at a constant value. I'm going to fix it at 25. And then I'm going to experiment with the pressure. So this is 25. So I'm holding the temperature constant across here, and I'm going to take some experimental readings. There's enough data points there that, well, I could fit a line or a curve through that, and I can find the point at which I see a maximum response. And the maximum response is going to be somewhere around there. So if we just put some numbers on here, if you look at this region here, that's about 1300, and then we come up to about 1500, and then here we have, that's also about 1500, and then it comes down to about 1400. So this point here is just under 1600, but let's call it 1600. That's where the maximum is, and that's probably around about pressure of about 21. So now we're going to set this to be 21, and we're now going to experiment in this plane. Oops, let's draw it through that point. So this should be at P equals 21, so P equals 21. And I'm going to do a number of experiments along here. And based on that, I will find some sort of optimal condition, maybe around here. In fact, that's probably not true. It's probably going to be closer to something like here, to be honest. That's about 2100. So the optimal condition is something like 2100. And it's occurred when the pressure is 21 and the temperature is just under 49, say it's 39. So that's my optimization procedure using one factor at a time. Let's just compare that against the design of experiments. Well, with design of experiments, we actively search the entire design space by going to the corner points, and we had some measurements in the center, and there might be some measurements at other locations as well, but fundamentally we have those points covered off, and that's sufficient to describe this contour plot so that when we build a model, we would be able to identify this as the optimal condition. And that optimal condition is probably more like 2300, and that occurs at maybe the pressure equal to about 27 and the temperature at something like 45. So a couple of highlights here. First of all, we have failed in terms of finding the maximum condition, but also we identified a pressure of 21 to find the optimal condition, whereas here we're saying that actually the pressure is more like 27. So one factor at a time has missed the optimal location and the parameters required to achieve that optimal condition. Why has that happened? Well, it's happened for a very well-known reason. If you look at this contour map, it's got a diagonal associated with it. That diagonal is telling me that there's an interaction between the temperature and the pressure. That's to say that if I want to optimize the pressure, then I have to think about what level of temperature I have. If we do one factor at a time experimentation, we're not going to see that interaction effect. We're going to miss it. And therefore, those interactions will lead us to the wrong conclusions. Okay, so what I've tried to do there is to show you three different arguments that illustrate and justify statistically designed experiments. And they were all motivated around this idea of saying, okay, let's reverse engineer the analysis in order to think about the design. And in particular, we reverse engineer the statistical analysis. I just want to say a few words about the scope of design of experiments. I have illustrated these experiments in the context of scientific experiments, in the sense that the word experiment is associated with science. It's almost a definition. Science is, by definition, something in which you do experiments. If you can't do experiments in a discipline, then arguably it's not even a science. But more generally, design of experiments is used in process development. So when we are developing products and processes, so we want to understand products, we want to understand the processes by which those products are developed, are made. But design of experiments can also be applied to measurement systems. Typically, in measurement systems, we refer to it as gauge R&R, but the structure of a gauge R&R is a designed experiment. We can also think in terms of more complex measurement systems, such as assay development and analytical systems. So these are complex processes, and the key word there is a process. So the principles of applying design of experiments to processes is equally applicable when the process is an experiment, is a measurement system, such as an assay. If we think about a process as a black box, then we can think about the process as having inputs, that's to say process parameters, and outputs, which would be some type of product characteristic. And the goal of design of experiments is to understand the relationships between those inputs and the outputs. With screening designs, the goal is just really to determine, out of all of the feasible parameters, which are the most important ones. So we're just trying to pick out the most important ones. With a response surface design, what we are trying to do is say, okay, we know what the important ones are, but let's model the detailed characteristics. So response surface designs allow us to model, for example, this curvature, which we wouldn't typically see in a screening design. What the screening design tells us is that this has got a strong effect, whereas this has got a moderate effect, and this has got no effect. And that assessment would be equally true here, even though we didn't maybe model the curvature, we could still establish that there's a strong effect for that parameter. So to summarize then, we use design of experiments to identify parameters that are critical to a product quality. We can use the technique to optimize performance, and we can use design of experiments to develop robust processes.